Hello everyone, this is Yi-Yang Wang, M1 student from Ogji Lab. Today, I would like to introduce his research called Impacts of Shared Autonomous Vehicles, Trade-off between Parking Demand Reduction and Congestion Increase. At first, let me talk about the background and objective. Shared Autonomous Vehicles, or SAVs for short, have advantages and disadvantages. They can reduce parking demand by replacing private vehicles, but may also increase congestion by generating more empty fleets. So, consider the future condition that all private vehicles are replaced by SAVs. We'd like to know that, first, which type of land use will reduce the parking demand the most? Second, in which part of the road network will the congestion increase the most? Thus, our objective is to estimate such impacts of SAVs at the local scale by simulating their operations. Then comes to the simulation framework. We set two scenarios, an SAV scenario with 100% SAVs and a current situation with 100% private vehicles. The structure is as follows. There are three main modules: a demand generator, an SAV dispatcher, and a traffic flow simulator. The demand generator generates travel demand at every time step, and the SAV dispatcher updates SAV assignment if new demands occur. Finally, the traffic flow simulator updates traffic flow and then enter the next time step until the end of the simulation. We should note that the area is divided into zones according to land use, and parking demand is estimated using different methods for two different scenarios. The researchers conducted a case study in Okinawa mainland and used Nara City with surrounding zones as the study area. The simulation observed a reduction in parking demand, with the reduction in periphery zones much larger than that in core zones. When regarding the land of use, office-dominated zones reduced the most, followed by residence-dominated zones. A congestion increase is also observed. We used the three indexes to evaluate the congestion, and the results showed that vehicles' kilometer traveled and delay time increased, while average travel speed reduced. Similarly, proportion of increased delay time increased more in periphery zones than core zones. Finally, we would like to discuss the reasons for above phenomenon. We think that smaller SAV fleet size and efficient movement of SAVs contribute to the parking demand reduction. For increased congestion, it's because the long empty fleets and detour behavior of SAVs and differences in the traffic capacity of a road network and the spatial density of SAV stations lead to heterogeneity between core and the periphery areas. Now, we can answer our questions that SAVs reduce parking demand greatly in office and residence zones, and increase traffic flow mostly in periphery areas. We suggest that urban planners should balance the pros and cons from the two factors, otherwise reorganize the traffic system to totally remove detriments. That's the end of my introduction. Thank you for listening.